Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Starting with the name of Allah subhanahu wa ta'ala, the most merciful and the beneficent. In the previous week lectures, we discussed that how we can represent a system in time domain, that is time domain modeling. And finally, we come up with a state space representation, that how we can represent a system in the state space. Similarly, in this week we will discuss that how we can find the state space representation of all three types of system, that is mechanical rotational system, mechanical translational system and the electrical systems. This is our first mechanical rotational system in which we will want to determine that state equation of this system, and the output quantity is the angular velocity at this point omega 2 theta 2, angular velocity omega 2. So for representing this system using state space representation, first step is to draw a free body diagram. Here we have two nodes theta 1 and second node is theta 2. So start with the free body diagram. At node theta 1 I have an input torque. At this similar point I have a moment of inertia J1. Similarly, at this point I have a damper here. This is my damper. I will write it as B1. And I have a spring in between two nodes theta 1 theta 2. So I will denote a spring here between two nodes at theta 2. I have another moment of inertia and a damper. So I will connect a moment of inertia, similarly damper here. So this is my reference node, this is my input torque T, this is J1, this is my B1, this is J2, this is B2, and this is basically my spring K. This node is theta 1, this is theta 2. So first of all we have drawn the free body diagram. Now we want to write the node equation. So I can write at node theta 1 the input torque is basically T, and the reactive torque due to this input is torque due to J1 plus torque due to B1 plus torque due to K. This is my equation number 1. So at theta 2 I can write another equation which is at node theta 2 the input torque is basically the torque due to this spring K, and the reactive torque will be torque due to J2 plus torque due to B2. This is node A. This torque will transfer to this node via this spring Tk, and these are the reactive torque due to this input. So this is my equation number 2. Now we want to write state variables here. The state variable here in this question will be two state variables for these two masses, and these two displacement will be the state variable for this spring. So I will mark this that I want to write now state variables. State variable. My first state variable will be x1 is equals to theta 1 x2 is equals to omega 1 Similarly, x3 is my theta 2 and x4 is equals to omega 2. I can evaluate x1 dash directly from the x2, which is d theta 1, and theta 1 is basically d x1, which is x1 dash. This will result in equation x1 dash is equals to x2. This is my equation A, the first state equation. Similarly, d theta 2 or x3 dash can be evaluated directly from here, that omega 2 angular velocity can be written as change in acceleration d theta 2. So this is theta 2, which is equals to dx3, which is x3 dash, and it can be written as x3 dash is equals to x4. This is my second state equation. I will say it equation B. And now we want to find x4 dash and x2 dash. What we want to evaluate is x2 dash, which is d omega 1. We need to know it yet. x4 is d omega 2, and we didn't know. So using equation 1 and 2, which we evaluated earlier, that is equation 1 and 2, we can evaluate this omega 1, d omega 1, d omega 2 means x2 dash and x4 dash. We can easily see that from equation 1 we have J1, this torque will be mathematically written as J1 alpha 1. Alpha is basically the acceleration, which can be written as in terms of velocity d omega 1. Change in velocity is basically the acceleration. So d omega will be evaluated from the equation number 1. Similarly, d omega 2 will be evaluated from the equation number 2. So for x2 dash, I will be using equation number 1. Using equation number 1, which is, okay, we have to define a state variable of input as well, which is u is equals to t. Input torque is basically represented as u. So equation number 1 was torque is equals to torque of J1 plus torque of B1 plus torque of K. This is torque J1 alpha, or alpha can be written in terms of omega, G omega 1 plus B is B1 omega 1, K is present in between theta 1 minus theta 2. So these are the equations. This is the equation which from which we can evaluate x2 dash, which this is x2 dash. X2 dash is this. So I can transform this equation with the help of a state variable. No system variable will be available now. We will just replace all the system variable omega, theta 1, theta 2 with the state variable. So the input t is basically u here. This is J1 x2 dash plus B1 omega 1 is basically x2 plus K, theta 1 is x1 minus theta 2 is x3. So I can evaluate x2 dash from here. X2 dash, just rearranging this equation, this will become minus K over J1, so minus K over J1 x1, any x2 term, yes, minus B1 over J1 x2, x3 will be plus k over j1 x3 plus u over j1. This is my x2 dash. I will write it equation C. Similarly, we want to evaluate x4 dash. x4 dash can be evaluated using equation 2. Using equation number 2. Equation number 2 was Tk is equals to torque due to J2 plus torque due to V2. Just look at that equation 2. This is Tk, the input torque, which is equals to Tj2 plus Tv2. This K can be written in terms of K theta 1 minus theta 2. Torque at J2 is basically J2 alpha 2 can be written in terms of omega d omega 2. Change in velocity is basically my acceleration. V2 is basically d2 omega 2. So changing all these system parameters with the state variables, theta 1 is basically x1 kx1 minus kx3 is equals to j2 d omega 2 is basically x4 dash plus v2 x4. So our x4 dash can be evaluated. Just rearrange this term. This will be k over j2 x1, no x2 term, x3 is minus k over j2, similarly minus b2 over j2 x4. This is my equation D. This is my equation. So all four state equations are now available here. x1 dash, x2 dash, a and b, x1 dash and x3 dash, x2 dash is here and x4 dash is here. So all four state equations are known now. We can write these state equations as state space representation. State space representation, the generalized format for state space representation is x is equals x dash is equals to ax plus bu. Here it has x1 dash, x2 dash, x3 dash and x4 dash is equals to, for x1 dash we can see here x1 dash is equals to x2 and x3 dash is equals to x4. So we can write x1 dash didn't depend on x1, so this is x1 depends on x2. x1 dash is equals to x2 this will be x1, x2, x3, x4. x1 dash is equals to x1 dash is equals to x2. So we can read it, draw by column multiplication, no x1, x2, x3, no x3, no x4, so x1 dash is equals to x2. For x3 dash is equals to x4. So what we can write will be 0, no dependency on x1, no dependency on x2, no dependency on x3. Yes, x4 is present in x3 dash. x3 dash is equals to x4. For x2 dash and x4 dash we can use equation C and D. x2 dash is equals to minus k by j1 minus b by g1, coefficient of x1, coefficient of x3 and coefficient of x2. So we can write minus k over j1, this is my x1 coefficient, minus k over j1 minus b by j1, or k and k by j1. This is minus b by j1, this is k by j1, no dependency on x4, no x4 is present, u is present, we will write it later. So x4 dash, yes, there is a coefficient of x1 which is k over j2, k over j2. Similarly, we have this term is basically x1, x3, x4, this is x3. So we will write no terms of x2 minus k by j2 x3 and minus b by j2 minus b by j2 x4. This is basically my state space representation plus b u. There is u is only present in equation C of x2 dash, no u in x1 x3 dash, no u in x4 dash. So we have x1 no dependency on u, x2 no dependency, yes, in x2 we have a dependency which is equals to 1 over j1. The coefficient of u is 1 over j1. So I will write here, this is 1 over j1, no dependency in x3, no dependency on x4. So x1 dash is equals to only x. So this is the state space matrix which we used to write in the state space representation. And finally, we want to write the output equation. Our output equation is y is equals to, here in the question it is given that our output is basically omega 2. Omega 2 is our state variable x4. So I will write our output is basically no x1, not x2, not x3, x4. It is x1, x2, x3 and x4. So this is basically the final state space representation in which you represented this whole system with the help of this state space representation, and I think this is no more difficult thing. If you have any queries, you can ask it in live session. This is the second example of mechanical rotational system in which we will discuss that how we can determine the state equation of the system. Here theta 3 is our system output. Theta 3 is basically the angular displacement at this node 3. This spring K1 effectively not in the system because the torque is transmitted through this spring. What does it mean? We will discuss it in this example. The first step to represent this system, to find the state equation, is to form the free body diagram. We have three nodes here, theta 1, theta 2 and theta 3. So we can draw a free body diagram here. At theta 1 we have input torque which is equals to the torque of spring K1. So I will draw, this is my input torque, this is my input torque P, and this is my spring K1. Here we have a moment of inertia, and this is my basically node theta 1. This is my spring K1. This spring is transferring this force to this node theta 2. At this theta 2 we have J1, B1 and B3. So this is my moment of inertia J1. This is my input torque T. And at this theta 2 we have B1, which is basically our damper. And a B3 which P3 is basically a damper which is transferring this force from point theta 2 to this theta 3. This is my B3. This is my node theta 3. At theta 3 we have J2, A2 and this B2. This is my second moment of inertia. This is J2. Similarly we have here a damper B2 and a spring K3. This is my reference node. This was my damper B1, this is B2, this was K2 and this is basically B3. This is basically a free body diagram of this system. We can now write the torque equation at different nodes with the help of this free body diagram. At node theta 1, at node theta 1 we have input torque T, which is equal to the torque of this spring. This is input torque at theta 1 and this is basically the reactive torque. So this is my input torque T and this is my reactive torque T K1, which is equals to K1 theta 1 minus theta 2. I will say that this is my equation number 1. Similarly, we can write equations at different nodes theta 2 and theta 3. At node theta 2, the input force is this force due to the spring and these are the reactive forces at node theta 2. So we have input force which is equals to Tk1 and the reactive forces are basically theta 1 torque due to J1 plus torque due to B1 and torque due to this is my equation number 2. At node theta 3, at node theta 3 we have input force due to this damper, torque due to this damper, and these are the reactive torques at this node. So this will be torque of J2 plus torque of B2 plus torque of K2. This is my equation number 3. So these are the 3 equations. Here we can see this input torque is equal to the torque produced by this spring. So we can say this spring is just transferring this input for torque from here to here. So here this means that this is no more effective part of this system. This is just transferring this input force to this node. This is written here. The spring K1 is effectively not in the system because the torque is transmitted through this spring. So here what I can do, this is spring force is equals to the input, so I can replace directly here the Tk1 with the input, which means that in this system we didn't have any, this is no more effective part. So the spring K1 is no more our effective part. So what I can write, if I want to find the state variables here, first of all I would like to write this equation using equation 1 and 2. I can write torque K1 is equals to torque of J1 plus torque of B1 plus torque of B3. This is my equation 4. So these are the equation, and now we can find the state variable. For state variables, how to select the state variable? Here we have moment of inertia 2, moment of inertia 1. Moment of inertia basically stores energy due to the angular velocity. So if we see here in the diagram, this moment of inertia is present at theta 2 or node 2. So omega 2 is our state variable because moment of inertia stores energy due to this omega 2. Similarly, omega 3 will be our state variable because we have a moment of inertia at node 3. Similarly, we have a K2 energy storing element spring at node 3. So theta 3 basically angular displacement is our state variable. K1 is no more effective part, so we didn't have any other state variable. So we will have 3 state variable: omega 2, omega 3, and this theta 3. So I have state variable 1 x1. X1 will be equals to theta state variable x1 is equals to my theta 3. Similarly, I have x2 which is equals to omega 3, and I have x3 which is equals to omega 2. This is because of spring 2 K2, this is because of moment of inertia J2, this is moment of inertia J1. So these are the 3 state variables. I can find x1 dash directly from here, which is equals to d theta 3. Basically change in displacement is equals to velocity, change in angular displacement is equals to change in angular displacement is equals to angular velocity. So I can write it as x1 dash. So my this equation yields x1 dash is equals to x2. I will write that this is my equation A. For evaluating x2 dash and x3 dash, x2 dash is basically x2 dash is d omega 3 dash, which is unknown right now. Similarly, x3 dash is d omega 2, which is unknown. So we can find these parameters from equation 3 and 4 using equation number 4 first. 4 which is equals to, okay, here we have input which is usually represented by u in the state variables. So using equation 4, which is equals to T is equals to torque due to J1 plus torque due to B1 plus torque due to B3. This is my equation 4. So I can write this torque due to J1 can be written as J1 d omega 2. This is because at node 2 I can write d omega 2 alpha 2. Alpha 2 means angular acceleration, which can be written as d omega 2 plus b omega 2. Basically this is damper. Mathematical model of damper is b omega. At node 2 we have b omega 2. Similarly, b3 is basically present in between node 2 and node 3. So we will write it. This is b1 this is my B3 is equals to omega 2 minus omega 3. So I will try to transform this equation in which no system parameter will be present, only state variables will be there. So I will replace this t with state variable u. This is my j1 x3 dash plus b1 omega 2 is basically x3 plus b3 omega 2 is my x3 on omega 3 is my x2 b3. Look at here, x2 is omega 3 and x3 is omega 2. So I can find x3 dash by rearranging this equation. This equation will become, we have x2 term here, b3 over j1 is equals to b3 over j1 into x2. Similarly, we have two x3 terms here, which will be minus b1 plus b3 over j1 x3 and a u here, u by j1. This is my equation. B. Okay, we have now x3 dash, we want to evaluate now x2 dash. So using equation number 3, which is basically torque B3 is equals to torque of J2 plus torque of K2 plus torque of B2. Let's see this equation. This is equation number 3. Torque of B3 is torque J2, B2 and K2. So torque of B3 is basically B3 present in between node omega theta 2 and theta 3 omega 2 minus omega 3, and torque at J2 is basically J2 D present. This moment of inertia is at node 3, so we will write omega 3 plus torque of K2 is K2 theta 3 plus B2 is B2 omega 3. This is my x2 dash. I can evaluate x2 dash by replacing all these system parameter with the state variable. This will become B3 omega 2 is x3 minus omega 3 is x2 is equals to J2 x2 dash plus K2 x1 plus B2 omega 3 is x2. x2 dash will be equals to K2 over minus K2 over J2 x1, no, yes, x2 term is there, minus B2 plus B3 over J2. This will be x2, these two x2 terms, x1 and x3 term, B3 over J2 is x3. This is my equation C. So we have evaluated all three x1 state variables, x1 dash, x2 dash and x3 dash. Now we want to write it in this state space representation. So this state space representation will be x1 dash, x2 dash and x3 dash. In which this is x1, x2, x3 plus u. So if we see x1 dash is available here, which is equals to x2, no dependency on x1 and x3, so x1 is 0, x3 is 0, only equals to x2, no dependency on u. Similarly, x2 dash is here, which is equals to minus k2 over j2. Basically the coefficient of x1 is minus k2 over j2 and the coefficient of x2 is minus b2 plus b3 over j2, x3 b3 over j2, no dependency on u. For x3 dash we can see this equation here. x3 dash is basically no dependency on x1, b3 over j1, x2, x3 and u, b3 over j1, x3 dash no dependency of x1 minus b3 over j1, x2, plus similarly b1, b3 over j1, b1 plus b3 over j1. This is the x3 and 1 over j1 is u. 1 over j1 is u. This is minus. So this is basically my state space representation of the system. Here output is theta 3, y. Theta 3 is my state variable x1, so I will write 1, 0, 0, x1, x2 and x3. So this is my theta 3, so my output is at theta 3 and these two values will be 0. This is my output equation, this is my state space representation. I hope that this question is clear to you. If you have any problem regarding this question, you can ask in the live session.